We can also look at the idea of higher order partial derivatives. If f is a function of two variables, then f of x and f of y are also functions of two variables. As such, we can consider partial derivatives of higher orders, which are simply partial derivatives of the first order partial derivatives. So, as an example, if I have the partial with respect to x, I can take that again with respect to x, which is very commonly simply written as f sub xx. But this is actually the partial with respect to x of the partial of f with respect to x, which would then be the partial squared or the partial of x squared. And of course, you can also write this as z if you wanted to. Likewise, I could take a look at the partial of y with respect to y, which I would write as fyy. And that's the partial with respect to y of the partial of f with respect to y, which is obviously using the same notation. No surprise there. But where things get kind of fun is, what if I take the partial with respect to x and take the partial of that with respect to y? Well, that would then be fxy, which is the partial with respect to y of the partial of f with respect to x, which is going to be, whoops, that's not what I wanted. I need the partial squared of f partial of y, the partial of x. Now, reading this, you got to be careful when you read these notations, because this is saying this is the partial of x, and then I'm going to take the partial of y. So this is actually going, in a way, left to right in terms of how do I calculate this. I go left to right. So I can find the partial of x first, then take the partial of y of that partial I just found. This one, you're going to be reading right to left. This is saying find the partial with respect to x first, then once you found that, find the partial with respect to y. So that's going right to left. This is going left to right. So make sure you understand the order in which you could be taking these derivatives. Let's see, now using similar notation, I can take a look at the partial of y and take that with respect to x, which would be f of yx, which is the partial with respect to x of the partial of f with respect to y, which I would again write as this. There we go. So that should be no big surprise. Now, some books also use notation for fxx as f11 and fyy as being f22. fxy would then be f12, and fyx would be f21. Now that notation I find kind of confusing, but you may see it sometimes. And where this comes from is if I do a grid like this, now in terms of matrix, this is row 1, column 1, this is row 1, column 2, this is row 2, column 1, this is row 2, column 2, and that reads off my derivatives. The partial of x with respect to x, xx is 1, 1, that's that one. X then y, that's 1, 2, that's x then y. Y then x, that's 2, 1, so that's y then x. And y then y is 2, 2, so that's y then y. So I do find that personally that notation kind of confusing, and I'm quite certain you will never see me actually use it, but you could see it someplace. So it wouldn't hurt if you knew what that meant. Now, obviously, I can go even further with this. I could do the partial with respect to x and then y with respect to perhaps y. That I would write as f x, y, y, which is, if you follow the way I said that, I'm going to have the partial with respect to y of the partial with respect to y of the partial of f with respect to x. So that, working inside out, would actually give me exactly what I asked for here. And another way that I could write that would be simply to say that this is, see, there's 1, 2, 3 of them. And then there's 2 of the y's, so there's partial y squared and then the x. And again, here I'll be reading left to right. So I need to find the partial of x with respect to x, then find it with respect to y, then find it with respect to y again. Here I'll be reading right to left, so I need to find the partial with respect to x. Then I'm going to find it with respect to y, and again with respect to y. So let's go ahead and work through a quick example. So let's see, given f of x, y equals x times e raised to the yx, I want to find the following partial derivatives. The first one is I want to find fxx. Well, that's going to be equal to the partial with respect to x of the partial with respect to x. So let me see, the partial with respect to x here is going to be the product rule. I have 2 functions of x. So it's going to be e to the yx plus yx times e to the yx. So that's my first partial. Now I need to take the derivative of this, once again, with respect to x. And so that's going to actually give me y times e to the yx plus, remember this is in respect to x, so a product rule again. So my constant is y times e to the yx plus, again with respect to x, I'll have y times x, but I'm going to have the derivative of this exponent. So that's going to give me y squared x e to the yx, which I think I would probably collect some terms here. I would probably simply write this as y times e to the yx times, see there's 1, 2, how about y squared, whoops, I pulled out a y, didn't I? So I only have 1 y left. How about yx plus 2? Now the next one I want to look at is fyy. So that's going to be the partial with respect to y of the partial with respect to y. So here's my original function, and if I take the derivative of this with respect to y, I simply get x squared e to the yx. So I need the derivative of this again with respect to y, and that's going to give me x cubed e to the yx. Okay, I want to take a couple more here. So next I want to find, how about fxy? Well, that's the partial with respect to y of the partial with respect to x, and that was right here. So that's going to be the partial with respect to y of e to the yx plus yx e to the yx. So the partial of this with respect to y is going to give me x e to the yx. This is this first piece here, because remember, x is a constant. I have the product rule here. So this is going to be plus x times e to the yx plus yx squared e to the yx. Which, do I want to pull that out? Yeah. Let's pull out an e to the x, or x e to the yx. If I pull out that, I'll get x e to the yx times, well, there's 2 of them there, and I pulled out 1x, so how about yx plus 2? Then the last one that I want to look at, call this one D. I want to look at f yx. Well, that is going to be the partial with respect to x of the partial with respect to y, and that was right here. So I need the partial with respect to x of this guy, which I'm taking this with respect to x, so again I have that product rule. So this is going to be 2x e to the yx plus yx squared e to the yx, which if I factor out a x e to the yx, I end up with yx plus 2, which if you notice in this case is actually the same as fxy. So in this case, what we just showed is that fxy is equal to fyx. But I want to emphasize in this case, not necessarily in all cases. And actually, there's a theorem we're going to talk about, Clairaut's theorem, that says under certain conditions that this will actually always be true. So going back, fxx is right here. And then fyy is right here. fxy, we already boxed it. So here's my 4 partial derivatives from this function. Now obviously I could keep going and have all kinds of combinations, but I think these 4 examples work pretty well to give an idea how the partial derivatives actually work out.